All right, everybody, buckle up. We're going deep today, like really deep.
Deeper than deep.
You sent us this article, and wow, this one really gets into it. Space, time, dimension.
The fundamentals.
Yeah, and not just like the basics. This thing challenges some pretty big assumptions we tend to have, about how those things all work, especially time.
Right, and the way those concepts are being re-examined in modern physics is just incredible. I mean, it's changing how we see the entire universe.
Exactly. So we're going to try to unpack some of that today, get into some seriously mind-bending stuff from this article. Triangular models, Einstein, quantum physics, the whole shebang.
A lot to cover, but it's all connected and it's all fascinating.
Okay, so right off the bat, the article asks a question that seems super basic, but it really stopped me in my tracks when I read it.
Uh-oh, what's that?
It asks, what is time?
Whoa. Yeah, okay, I see what you mean.
Not just how we measure it, with clocks and calendars and stuff, but like, what is it really?
Yeah.
Right. So the article gets into these really interesting alternative views on time, like Ernst Mach, for example. He was this physicist and philosopher.
Oh, yeah.
He said time isn't some separate thing like a river flowing in the background. It's all about observing changes in the universe.
Makes sense in a way. I mean,
Yeah.
if nothing ever changed, would there even be time?
Whoa.
Right, it's a trip. And then you've got Gottfried Leibniz.
Another big thinker.
Yeah. He said time is really about the order of events, the sequence of things happening.
Like cause and effect?
Kind of.
Yeah.
Think about it. Your morning routine, the changing seasons, the evolution of the universe, it's all about the order things happen in, right? Not some big universal clock ticking away in the background.
Okay, so Mach is saying time has changed. Leibniz is saying time is order.
Yeah.
And both of them are basically saying Newton was wrong about absolute time, right?
Exactly. They're both pushing back against this idea of a fixed universal time, arguing for something more relational, more interconnected.
And then there's this whole thing about triangular models of time.
Oh, yeah. Those are fun.
They're pretty abstract. I'm still wrapping my head around them, honestly. But, help me out here. Imagine, you, your cat, and your coffee cup. Those are the points of a triangle. And as you move around, doing your thing, that triangle's shape changes.
Right.
And in this model, that changing shape represents time passing.
Because your relationship to your cat and your coffee is changing, so time is passing.
Yeah, so time isn't some separate thing, but it emerges from those relationships and changes between things. It's trippy.
It really is. It shows you how we take these basic concepts for granted. Like time, we just assume it's this universal thing, but maybe it's not.
Right. And then,
Yeah.
then, Einstein comes along with his theory of general relativity.
Boom.
And that's where things get really wild.
It gets intense.
Einstein basically shows that time isn't fixed at all. It's actually dynamic. Like it can be influenced by gravity.
Totally. Those massive objects like planets and stars, they're warping the fabric of space-time around them.
So time can actually be stretched or compressed, depending on how strong gravity is.
Pretty much. Imagine a bowling ball on a trampoline. That bowling ball's your massive object, the star. The trampoline is space-time.
Yeah.
The bowling ball creates a dip, right? That's the warping. Now roll a marble across the trampoline.
It'll curve as it gets close to the bowling ball.
Exactly. That's like how light bends around massive objects in space. And because light travels through space-time, well, that means time itself is affected by the warping.
Whoa. So time is like part of this flexible fabric of the universe that can be stretched and squished. That's crazy.
Super crazy. But, and here's the thing, quantum mechanics kind of throws a wrench in the works.
It's another wrench.
Another wrench. Paul Dirac, a big name in quantum physics, he wasn't entirely on board with how flexible space-time could be in Einstein's theory.
Interesting.
He was worried that if space-time was too flexible, you wouldn't be able to say for sure that two events, even way far apart, happened at the same time.
But doesn't Einstein's theory say that simultaneity is all relative anyway? Like, two people moving at different speeds might disagree on whether two events happened at the same time.
You're right, that's special relativity. But Dirac was thinking about a future theory that could unify general relativity with quantum mechanics, a theory of quantum gravity. And for that, he thought we might need to bring back the idea of absolute simultaneity, at least in some sense.
So, tension between special and general relativity when you throw quantum mechanics into the mix.
Big time tension.
Okay, that's a lot to process.
Yeah.
So this isn't like settled science, right? There are still some big questions here that physicists are trying to figure out.
For sure, special relativity works great locally, but general relativity and quantum mechanics, that's the big challenge.
Got it. Okay, let's shift gears for a minute. Back to Mach's principle. Something about how the entire universe determines, what were those called?
Inertial frames.
Right, inertial frames. But first, remind me, what is an inertial frame?
Basically, it's like your perspective when you're moving at a constant speed in a straight line. Like, imagine you're on a train. If you don't look out the window, it feels like you're not moving at all, right?
Yeah.
That's being in an inertial frame. And Mach's principle says that even that experience, that feeling of motion, is determined by all the stuff, all the matter and energy in the entire universe.
So even though it feels like we're moving through space,
Yeah,
our experience is actually shaped by, like, everything.
pretty much.
Wow. And this is all connected to Newton's idea of absolute space.
Yeah, Mach, like Leibniz, was not a fan of this abstract space idea. They thought space is better understood in terms of distances and relationships between things.
So instead of this big empty container that stuff just sits in, space is more about how things are connected to each other.
More like a web of relationship.
Okay, so this has all been super fascinating, but I got to ask, what does it all mean? Why should we, like normal people who aren't physicists, care about these debates about space and time?
Well, the article touches on some really cool implications. Like, there's this idea of complexity growth as a way to measure time. It's different from entropy, which is about things getting more disordered. Complexity growth looks at how interconnected and complex things are becoming over time. It's like a new way to think about time itself, especially in fields like cosmology and biology.
So instead of just measuring time with a clock, we could measure it based on how complex things are getting.
Exactly.
That's pretty mind-blowing.
It really is. And Mach's ideas, they're still super relevant today. They're shaping new theories that are connecting the vastness of the universe with what we observe right here, right now.
And this whole thing about quantum gravity, does that tie in too?
Absolutely. Trying to unify general relativity and quantum mechanics is forcing us to rethink how deeply connected space-time really is and what simultaneity even means on a fundamental level. Like, it might not be as simple as we think.
Okay, that was a lot. I feel like we just went on a roller coaster ride through the most fundamental concepts in physics.
That's a good way to put it.
We started by asking, what is time? And ended up, I don't even know where we ended up.
We ended up questioning everything.
Pretty much.
But that's what it's all about, right? Asking those big questions. Like, if our experience of time is all about change in the universe, what would happen in a universe where nothing ever changed?
Whoa. I have no idea.
Oh.
But I'm going to be thinking about that one for a while. Thanks for joining us for this deep dive into space, time, and dimension.
Absolutely. And thanks for sending us this article.
Until next time, keep those minds curious.
Stay curious.